A 500-year-old wall can survive an earthquake that destroys a modern city. This is not a legend, but the enduring reality of Inca stonework, a feat of engineering that has some of the most powerful forces on our planet. By the end of this exploration, you will understand the precise interlocking stone technology that makes these ancient walls earthquake-proof. We will uncover how stones cut with impossible precision can dance through a tremor without crumbling, and what hidden intelligence in their design we have only begun to appreciate. What does true resilience look like when it is carved in stone? The ground beneath the Inca was never truly still. It was a land shaped by immense, unseen pressures, where the continent itself is slowly being forged anew. This is the Andes mountain range, a place of breathtaking beauty built upon one of the planet's most active geological fault lines. Here, tectonic plates grind against each other with a force that can reshape landscapes in an instant. For the Inca, whose capital city sat directly atop this restless foundation, the threat of a devastating earthquake was not a distant possibility. It was a recurring chapter in their history, a fundamental condition of their existence. Imagine building a civilization, not on solid rock, but on a foundation that could, without warning, begin to shudder and roll like a wave. This was their relentless reality. It created a powerful imperative, one that transcended mere aesthetics or even spiritual symbolism. Every structure, from the humblest storehouse to the most sacred temple, had to answer a single, brutal question. Could it withstand the next great shake? This environmental pressure is the essential key to unlocking their genius. They were not simply stacking stones, they were engineering for survival, devising a form of resilience written directly into the bones of their cities. Their architecture became a dialogue with the unstable earth, a conversation in stone that we are still learning to interpret. The solution they crafted stands in direct opposition to the way we build today. Modern construction is founded on the principle of rigidity. We bind materials together with cement, mortar, and steel to create a single, unyielding mass. The logic seems sound, to make a structure so solid it cannot be moved. But the Inca understood something profound about the nature of the ground they lived on. Fighting that movement was a battle they could never win. So they chose a different path, one defined by a single, radical principle: the complete rejection of mortar. They used no cement, no binding paste of any kind. Instead, they pursued a level of stonework so precise it defies belief. Each block was painstakingly shaped, not into perfect rectangles, but into unique, multifaceted puzzle pieces. The goal was a fit so tight that even the thin blade of a knife could not slip between the stones. This was not merely for show, it was a deliberate engineering choice. A mortared wall is monolithic. It moves as one unit. When the ground shakes, that rigid structure tries to hold its form, but the forces are too great. Stress concentrates at the weakest points, the mortar joints crack, and the entire assembly can shatter or topple. An Inca wall, however, is not one thing, it is a collective. Each stone is an individual, locked in place by its neighbors through geometry and friction alone. When an earthquake strikes, that rigid unity becomes a fatal flaw, while the flexible collective becomes a brilliant adaptation. The stones in an Inca wall can shift, they can rotate minutely, they can settle and resettle, all without losing their structural integrity. They do not fight the earthquake, they absorb its energy and dissipate it through countless tiny movements. Think of it not as a wall breaking, but as a wall breathing, a living, dynamic entity that rides the wave of a tremor. This foundational idea, building for flexibility instead of rigidity, sets the stage for the even more intricate intelligence hidden within each uniquely shaped stone. This principle of flexibility is brought to life in the very shape of the stones themselves. You will not find a single, perfect rectangle in a true Inca wall. Instead, you are looking at a field of irregular polygons, a collection of stones with 5, 6, 8, or even 12 distinct sides. Every single block is a one-of-a-kind masterpiece of geometry, shaped not to a standard template, but to fit the exact negative space left by the stones already set around it. This is not random chaos, It is a deliberate and incredibly sophisticated form of construction. Think of it as a three-dimensional stone puzzle assembled without a picture on the box. The builders were working with a dynamic, living model, where each new piece had to be custom carved to interlock perfectly with the complex contours of its neighbors on every side, top, bottom, left, and right. The result is a wall where the stones are held in place not by glue, but by a perfect marriage of geometry and gravity. Each block is cradled by the ones around it, locked in a gentle, unyielding embrace created by its own immense weight and the counter pressure from every adjoining face. This intricate design has a profound engineering consequence. In a wall of uniform bricks, a seismic shockwave can travel in a straight, devastating line, creating a single, catastrophic crack that splits the structure in two. But in an Inca wall, there is no straight line to follow. The force of an earthquake hits a labyrinth. The energy is forced to travel along a zigzagging, twisting path through that intricate network of interlocking joints. With each turn, with each redirection, the destructive power is dissipated, scattered, and absorbed until it simply fades away. The entire wall behaves not as a brittle slab, but as a unified, flexible mass that can sway and settle as one. It is a concept of distributed strength that feels remarkably modern, yet it was being executed in stone centuries ago. But this leads to an even more pressing question. How did they achieve such impossible precision with nothing but stone tools and human hands? The answer lies in a process that was less like construction and more like a careful, ritualistic form of fitting. The true secret lies not in a single tool, but in a philosophy of work that transformed stone into a collaborative partner. To achieve those seamless joints, the Inca stonemasons engaged in a dialogue with the very rock they were shaping. It began at the quarry, where massive blocks were carefully selected and rough-shaped using simple but effective tools, harder stone hammers and durable bronze chisels. The initial form was created there, but the final, impossible precision happened only at the wall itself, in a meticulous ritual known as ashlar masonry. This was not a process of rapid assembly. Each uniquely shaped stone was brought to its intended place and carefully offered up to the gap it was meant to fill. It would not fit, of course. The masons would then lower the block and examine the contact points, identifying the high spots where rock touched rock. Using handheld abrasives, often just sand and water or a simple stone tool, they would patiently grind away only those microscopic points of contact. Then they would lift the stone again, test the fit, lower it, and abrade a little more. This cycle of trial fitting and incremental subtraction could be repeated dozens, even hundreds of times for a single stone. It was a dance of supreme patience, where the goal was not to force the stone into a preconceived shape, but to allow the two surfaces to find their own perfect union. The mason was not a dictator to the material, but a mediator, listening to the stone's feedback, the scrape and grind that told him where to remove the next minuscule grain. This subtractive art form required a deep, intuitive understanding of the stone's properties, its grain, its hardness, and its points of stress. The final product, that knife blade tight joint, was born from this intimate, time-consuming conversation between human intention and geological reality. It was craftsmanship elevated to a form of reverence, where the builder worked in harmony with the earth to create something that could withstand the earth's own fury. Yet this painstaking process only explains how the stones were fitted together. It does not reveal the master blueprint, the guiding intelligence that dictated the shape of each irregular polygon in the first place. How did they know what final form to pursue? The true puzzle begins long before the stones ever touch each other. How do you move a block of granite weighing more than a full-grown elephant across dozens of miles of the most rugged terrain on Earth, and then lift it precisely into place on a steep mountainside? The quarries were often far from the construction sites, separated by deep ravines and sheer slopes. There are no records of wheels or pulleys, and the Inca had no draft animals capable of such a load. The solution was a breathtaking feat of logistics, a testament to an organizational mind that saw human coordination as the ultimate technology. Evidence points to a combination of simple, brilliant physics and immense, coordinated effort. They likely built earthen ramps, packing soil and stone to create gradual inclines up to the rising walls. They would have used log rollers, placing the massive stone on a track of felled trees, with teams constantly moving the rear logs to the front in a continuous, painstaking cycle. Levers, ropes, and the raw power of hundreds of people would provide the motive force. Some researchers propose even more intriguing ideas, like the potential use of sound or rhythmic vibration to momentarily reduce friction, making the stone slightly easier to shift, though this remains in the realm of theory. The undeniable engine behind it all was the system, a form of labor tribute that was the backbone of the Inca state. This was not slavery, but a rotational duty where communities contributed work to state projects as a form of tax. It created a vast, organized workforce of thousands, all directed with military precision. Imagine the scene, a river of people moving in unison, chanting in rhythm to coordinate their pulls, guided by overseers who understood the precise physics of mass and incline. This was social engineering on a monumental scale. The interlocking stone technology is not just in the walls we see, it is in the invisible network of human cooperation that made them possible. The precision of each stone joint is mirrored by the precision of the logistics that brought it there. One question, however, cuts through both the social and the physical mystery. With all this effort, with this obsessive pursuit of perfection, why did they leave so many stones visibly unfinished? Even the most perfectly fitted stones hold a deeper secret in their geometry. Look closely at a surviving Inca wall, and you will notice two subtle features that most eyes would miss. First, the entire structure is not perfectly vertical. It leans inward ever so slightly, like a pyramid with its top gently pushed toward the center. This is not a construction error. It is a deliberate design for mass and gravity. By inclining the planes of the wall, the builders lowered its center of gravity, making the entire structure more stable and resistant to toppling, much like how a wide-based pyramid stands firm, while a tall, thin column is easily knocked over. But the second, more ingenious feature is hidden within the joints themselves. Run your finger along the seam between two stones, and you might feel that the gap is not uniform. In many of the finest walls, the joints are meticulously tapered. They are cut so that the space between the stones is slightly wider on the inside of the wall than it is on the outside. To visualize this, think of a standard wooden wedge, the kind you might use to level a wobbly table. It is thick on one end and thin on the other. Now imagine that wedge shape embedded invisibly within the joint between two massive granite blocks. This simple taper creates a profound mechanical effect. During the violent shaking of an earthquake, as the stones are forced to move and shift against one another, this tapered geometry acts as a guide. Instead of pulling apart, the stones are driven inward along those inclined planes, wedging themselves and together with each tremor. It is a self-locking, self-centering mechanism built directly into the fabric of the wall. The earthquake itself becomes the force that reinforces the structure, actively making it more secure as the ground shakes. This is passive safety engineering of the highest order, a hidden intelligence carved into stone that requires no maintenance, no human intervention, and lasts for centuries. It turns a moment of potential destruction into an event of reaffirmation. The wall does not just survive the quake, it emerges from it stronger, its bonds reaffirmed by the very energy that sought to break them. This principle reveals a mindset that saw resilience not as a fixed state, but as a dynamic process, a conversation between structure and force. A masterpiece of stonework can be undone by a single overlooked detail beneath the surface. The Inca understood this fundamental truth of architecture, that true resilience is built from the ground up, beginning with what the eye never sees. Their process of site preparation was as meticulous and intelligent as their stone fitting. Before a single polygonal block was set, their builders became masters of the foundation. In many cases, this meant excavating through layers of loose soil and sediment until they reached the unshakable bedrock below. They were literally anchoring their structures to the bones of the continent, but bedrock was not always accessible. In these situations, they engineered stability, constructing deep, layered platforms of compacted earth and crushed stone, creating a solid, uniform base that would not settle or shift unevenly. This careful attention to the foundation ensured that when the ground shook, the entire wall would move as one coherent unit, rather than cracking apart as different sections settled on unstable or varied materials. Yet, they foresaw an even greater hidden threat than unstable soil, the silent danger of water. A foundation, no matter how well built, is vulnerable to the insidious work of erosion. More critically, during the intense vibrations of an earthquake, water-saturated soil can undergo a terrifying transformation known as liquefaction. In this state, solid ground temporarily behaves like a liquid, losing all its strength and bearing capacity. A structure built upon it can sink, tilt, or collapse entirely as its support literally flows away. The Incas' answer to this was a network of hidden intelligence, sophisticated drainage systems carefully integrated into their sites. They carved channels and conduits into the foundation layers themselves, designing them to capture rainwater and groundwater and channel it swiftly away from the base of their walls. This kept the foundational soil perpetually dry and compact, maintaining its structural integrity through the centuries. Their approach was holistic, viewing the wall not as an isolated object, but as the pinnacle of a carefully engineered system that began deep underground. It is a profound lesson in comprehensive design, reminding us that the most visible marvels of engineering are often supported by the most invisible and most critical feats of foresight. History delivered its verdict in the violent tremors of the earth itself. The arrival of the Spanish in the 16th century introduced a new architectural philosophy to the Andes, one built on the European tradition of brick, mortar, and precisely cut rectangular blocks. They constructed their churches, palaces, and administrative buildings with the confidence of their own technological heritage, often erecting them directly upon or adjacent to the enduring foundations of the Inca. For decades, these colonial structures stood as symbols of a new order. Then, the ground would remember its old ways. Major earthquakes struck the region in 1650, 1687, and 1746, each one a brutal, impartial test of the two competing visions of resilience. The results were stark and undeniable. Time and again, the rigid, mortared walls of the Spanish colonial buildings cracked, crumbled, and collapsed. Their bell towers toppled, their facades split open, and their roofs caved in. Yet just beside them, the ancient Inca walls, those intricate puzzles of interlocking stone, remained standing. They settled, they shifted, they danced with the tremor, but they did not fall. The polygonal foundations upon which some of the colonial buildings were foolishly placed often proved to be the only thing preventing total ruin. The city of became a living museum of this comparative experiment. You can see it today in places like the Church of Santo, built directly atop the sacred Inca complex of. The Spanish structure has required constant repair and reconstruction after seismic events, while the original curved, mortarless walls of the temple below emerge from every quake essentially unscathed. This is not a matter of opinion or legend. It is a physical, historical fact recorded in stone and rubble. The earthquakes acted as a ruthless laboratory, proving that the Incas' flexible, jointed system outperformed the imported rigid model in the very conditions the Inca had spent centuries mastering. It was a profound validation, written not in texts, but in survival and failure. This real-world case study forces us to ask a difficult question. If the technique was so demonstrably superior, why was it not adopted by the new rulers? The answer lies in a clash of worlds that went far deeper than masonry. The difference between the two walls is a lesson in physics written in stone. When an earthquake strikes, It sends waves of kinetic energy racing through the ground, a sudden, violent shove that seeks to topple anything in its path. A conventional mortared wall responds by trying to stand its ground as a single, rigid mass. It resists the motion, and in doing so, it concentrates all that immense force into a few critical points, typically the mortar joints between the uniform bricks. The energy has nowhere to go, so it builds until something gives way, cracking the mortar and shattering the wall's unity. It is a battle of brute force, and the wall, unable to yield, is almost always the loser. The Inca wall operates on a completely different principle, one of graceful dissipation. Because it is not a single entity but a cohesive assembly of individual interlocked blocks, the seismic energy does not meet a solid barrier. Instead, it meets a community in motion. The force of the shaking is converted into kinetic energy within the wall itself, transformed into countless tiny, permissible movements. Each polygonal stone can rotate minutely, slide fractionally, and settle against its neighbor. As they do this, the immense energy of the quake is spent as friction, the gentle grinding of stone on stone, and even as faint sound, a whisper of movement that replaces the deafening crack of failure. The wall does not resist the earthquake, it absorbs and disperses it, allowing the shockwave to travel along its labyrinth of joints until the force simply fades into harmless vibration. It is a dance, a dynamic fluid response where the structure sways and settles in rhythm with the tremors, emerging unified and intact. This ancient insight, building something that can move to avoid breaking, finds a direct echo in our most advanced seismic engineering today, in a technology known as base isolation, where entire buildings are set on flexible bearings to let them sway safely during a quake. The Inca, in their way, built base isolation into every stone. The stones may have been listening. Beyond the visible mechanics of interlocking joints and tapered seams lies a more subtle possibility, one that touches on the very nature of sound and vibration. Some researchers looking at the impossible perfection of these fits have wondered if the Inca were engineering not just for physical stability, but for acoustic harmony. The theory is compelling. When two surfaces are brought together with such precision, the interface between them changes how energy moves. In a wall built with this care, the contact points between stones are not rough gaps but continuous, intimate planes. This could fundamentally alter how sound waves, including the low-frequency vibrations of an earthquake, travel through the structure. Think of a tuning fork. When struck, it vibrates at a specific frequency, producing a pure, clear tone. Now, imagine an entire building acting like a giant, complex tuning fork during a seismic event. Certain frequencies of shaking could resonate within the structure, amplifying the destructive force. Much like an opera singer's voice can shatter a glass if it hits the exact right note. The intricate, irregular network of joints in an Inca wall might act as a natural dampener, scattering and absorbing those dangerous resonant frequencies before they could build to a breaking point. The wall would not just be resisting the quake, it would be actively silencing its most harmful voices. This idea ventures into the realm of speculative science, a fascinating frontier rather than a proven fact. We have no written records from the Inca explaining such an acoustic intent. Yet, whether by profound design or a spectacularly fortunate accident, the sonic properties of these structures are undeniable. In the quiet of a sacred site, the way sound carries, the absence of echo, the subtle hum one might feel when placing a hand on the stone, all hint at a material intelligence that interacts with the energy of the world in ways we are only beginning to measure. It suggests a worldview where a building was not a separate object, but an integrated instrument, potentially tuned to the fundamental frequency of the earth itself. This layer of mystery invites us to listen more closely to the past, to consider that the greatest feats of engineering might resonate on a level we have yet to fully hear. The stone itself was believed to be alive. This is the profound layer of meaning that transforms the Incas' engineering from a mere technical feat into a sacred act. For them, Architecture was never just about creating shelter or demonstrating power. It was a physical expression of their entire cosmos. The stones they worked with were not inert material, they were living entities with their own spirit and presence. The act of construction was not one of domination, but of respectful collaboration. When a mason spent weeks grinding and fitting a single block, he was engaging in a patient dialogue with the earth, listening to its form, honoring its nature, and inviting it to take its rightful place in a greater whole. This sacred perspective explains the otherwise incomprehensible investment of time and labor. The precision was not just for strength, it was a form of reverence. A perfect fit meant the stone was content, properly seated in a community of its peers, and the wall itself became a living tapestry of the landscape. This idea connects directly to the core social principle of a concept of reciprocal harmony and mutual obligation that bound their society together. Just as every member of the community had a role and a responsibility to support the collective, every stone in the wall had a unique shape and a vital role in supporting the structure. The wall was a microcosm of their ideal world, a physical model where each individual part, through its perfect fit, sustained the integrity of the whole. The stability of the empire and the stability of the temple were reflections of the same cosmic order. Building an earthquake-proof wall was therefore much more than a practical necessity. It was a spiritual imperative. It was an act of aligning human creation with the fundamental, often unstable, forces of nature, weaving a place of social and cosmic harmony that could endure even the world's tremors. This blending of profound belief with meticulous engineering may be the ultimate key to their success, for it motivated a level of care and patience that pure utility alone rarely inspires. The fortress of is where the rules of physics seem to bend. Perched on a hill overlooking, its colossal zigzagging walls are the ultimate expression of everything we have explored, executed on a scale that defies belief. Here, the polygonal stones are not merely large, they are titanic, with some individual blocks estimated to weigh well over 100 tons. That is heavier than a fully loaded commercial jetliner. Yet these behemoths are fitted together with the same knife blade precision found in smaller structures, creating sweeping, curved battlements that look less like a fortress and more like a petrified wave of stone frozen mid-crash against the hillside. The sheer scale amplifies every unanswered question to a deafening roar. How do you shape a 100-ton block of andesite into a perfect, multifaceted puzzle piece? How do you transport it, without wheels or pulleys, up a steep incline to its final resting place? And most critically, how do you then lower it into position with such delicate accuracy that it settles seamlessly against its neighbors? The logistics become a mystery as monumental as the walls themselves. This was not just construction, it was a form of geological alchemy, where the mountain itself was seemingly persuaded to reassemble into a new, more resilient form. The complex curves and sharp angles of the zigzag design are not merely for military advantage or artistic flourish. Engineers studying the site recognize a profound intelligence at work. Each inward projecting corner acts as a massive buttress, distributing the immense weight of the walls down into the bedrock in a stable, interlocking pattern. More importantly, that sawtooth shape is an indeflecting seismic force. When an earthquake's shockwaves hit a straight wall, they strike a flat, uniform surface. But when they hit zigzags, they encounter a series of oblique angles. The energy is shattered, reflected, and redirected along a chaotic path that robs it of its destructive power. The wall does not just absorb the tremor, it actively confuses and dismantles it. This site represents the absolute apex of the Inca building tradition, a monument that continues to baffle modern engineers. Its existence fuels theories about lost techniques or forgotten knowledge, a testament carved in 100-ton stones that whispers of a mastery we have yet to fully recover. That modular nature points to a fourth, deeply intelligent principle: redundancy. In a modern skyscraper, the entire structure often depends on a continuous steel or concrete frame. If a critical beam in that frame fails, the results can be catastrophic, as the load has no alternative path to follow. An Inca wall operates on the opposite logic. It has no single point of failure. Think of it not as a chain, where breaking one link destroys the whole, but as a net. Each stone is a knot in that net, supported by and supporting the knots all around it. If over centuries, one of these stones were to crack from freeze-thaw cycles or be intentionally out, the wall does not automatically crumble. The intricate interlocking geometry means the load that stone was carrying is immediately redistributed to its neighbors. The void becomes a localized event, not a systemic collapse. The surrounding stones, already tightly wedged against one another, simply take on a little more of the burden, their shapes ensuring the force spreads out along multiple new pathways. This is built-in resilience, a design that anticipates damage and contains it. It creates a structure that degrades gracefully over time, rather than failing suddenly and completely. This ancient insight into modular, redundant systems feels astonishingly contemporary. We see the same principle in the design of the internet, where information can route around a downed server, or in robust ecosystems, where the loss of one species does not cause the entire food web to unravel. The Inca, in their stonework, encoded a universal truth about strength, that true durability lies not in creating unbreakable parts, but in designing a system where the whole can survive the loss of any single part. Their walls teach us that sometimes, the most resilient structure is not a monolithic fortress, but a flexible, interconnected community, whether that community is made of stone, of data, or of people. Centuries after the last Inca mason laid down his tools, the world's leading seismic engineers have reached a startlingly similar conclusion. The most advanced earthquake-resistant buildings on our planet today do not stand rigidly against a tremor. They are designed to move with it. This modern philosophy, born from computer models and material science, finds a direct conceptual echo in those ancient polygonal walls. Take the principle of base isolation, a technology used in structures from San Francisco City Hall to hospitals in Japan. Instead of anchoring a building directly to the ground, engineers place it atop a system of flexible bearings, often made of layers of rubber and steel. When an earthquake strikes, these bearings allow the entire structure to sway and slide independently of the violent shaking below. The building essentially floats on a cushion of controlled movement. This is not so different from the way each interlocking Inca stone, free from mortar, could shift and settle minutely against its neighbors, allowing the wall to dance as a unified yet flexible mass. Both systems understand that trying to outmuscle the earth is a losing battle. The smarter strategy is to yield gracefully, to let the energy of the quake flow through and around the structure rather than into it. Then there are dampers, devices built into modern skyscrapers that act like giant shock absorbers. During a seismic event, these dampers convert the destructive kinetic energy of the shaking into heat or other forms of energy, effectively soaking up the force before it can stress the building's frame. This function mirrors the immense friction generated between those perfectly fitted granite blocks. Every tiny movement in an Inca wall, every microscopic slide and rotation, transformed the quake's violence into harmless friction and faint sound, dissipating the energy stone by stone. What modern engineering achieves with precisely calibrated pistons and viscous fluids, the Inca accomplished through geometry and mass. This parallel is a profound validation. It means the Inca builders, through generations of careful observation and empirical trial, arrived at a fundamental truth of physics that our own science has only recently with equations. Their technology was not primitive, it was predictive. They engineered a form of passive resilience that required no maintenance, no sensors, and no power source, yet it performed a function we now consider the pinnacle of seismic design. Their walls stand as a testament to a different kind of intelligence, one written not in textbooks, but in the enduring dialogue between stone and earth. Our most sophisticated tools meet their match against 500-year-old granite. With computer-guided lasers and diamond-tipped saws, we can cut stone with a precision the Inca could never have dreamed of. Yet when we try to replicate their signature achievement, the seamless fitting of massive, irregular polygonal blocks, something essential is lost in translation. We can create a perfect joint between two stones, but only if we first digitally scan both faces and then machine each one to a mathematically exact complement. The Inca method worked in reverse, shaping the second stone through patient, physical dialogue with the first. Our technology gives us the result, but it bypasses the profound, adaptable process that may have embedded a deeper kind of stability. More fundamentally, we lack the very conditions that made such work possible. We do not have the system, that vast, organized workforce for whom contributing labor to a sacred state project was a rotational duty and a social obligation. The economic model of their civilization, one where human time and effort on a monumental scale were the primary resources, is alien to our own. Our constraints are budgets, deadlines, and the cost of skilled labor measured in hours. Their constraint was the unwavering cultural imperative to build structures in harmony with an unstable earth, projects where the investment of decades was not a failure of efficiency, but a measure of devotion. This gap in our capability is a humbling lesson. It tells us that Inca stonework was not merely a technical skill to be reverse engineered. It was the physical expression of a holistic cultural project, where architecture held a paramount spiritual significance that motivated a level of patience and perfectionism we can scarcely comprehend today. Their technology was inseparable from their worldview, a reminder that some ancient achievements remain uniquely, magnificently products of their time. Laser light now maps what the eye cannot see. High above the dense forests of the Andes, aircraft equipped with LIDAR technology sweep over the landscape, sending down millions of pulses of light that pierce the canopy to reveal the ground beneath. This is not treasure hunting, it is a new form of archaeology, one that is uncovering the lost infrastructure of Inca ambition. Researchers are finding previously unknown quarries, tracing the ghostly outlines of ancient ramps and roadways, and mapping the full, staggering scale of their construction projects. These digital maps provide the first comprehensive blueprint of the logistical network that fed stones to sites like, showing us not just the destination, but the entire journey. On the ground, another tool is capturing the walls themselves in impossible detail. 3D photogrammetry involves taking thousands of overlapping photographs of a single wall face. Software then stitches these images together to create a hyper-accurate, three-dimensional digital model. This model can be rotated, measured, and analyzed down to a fraction of a millimeter. For the first time, we can see the true complexity of each polygonal joint, not as a flat seam, but as an intricate, three-dimensional landscape of interlocking contours. Every subtle taper, every intentional curvature, and every microscopic tool mark becomes a data point. This data is revolutionizing our understanding. Engineers are now feeding these precise digital models into seismic simulation software. They can apply virtual earthquake forces to a perfect digital replica of an Inca wall and watch, in real time, how the energy flows through that labyrinth of joints, how the stones theoretically shift, and where the stresses concentrate. It allows them to test the performance of these ancient designs against mathematical models of known quakes, moving our appreciation from awe into the realm of quantifiable engineering science. Each scan, each model, peels back a layer of the mystery. Yet, as with all profound research, every answered question seems to birth two new ones. The tool marks revealed by photogrammetry, for instance, show patterns that sometimes contradict our assumptions about the abrasion process. The sheer variety of joint designs, even within a single wall, suggests a level of adaptive, on-the-spot problem-solving that we are only beginning to decode. This creates a beautiful, ongoing dialogue. The past is no longer silent, it is providing new data. The present is no longer just guessing, it is asking sharper questions. The walls are no longer static monuments to a finished history. They have become active collaborators in a modern scientific investigation. They teach us a new lesson with every technological lens we train upon them, proving that the most enduring mysteries are those that evolve alongside our own curiosity. Granite itself breathes with the mountain's rhythm. In the thin air of the high Andes, the temperature does not simply change between seasons. It swings violently within a single day. Under the intense equatorial sun, a stone wall can become almost too hot to touch. Then, as night falls, the clear sky offers no blanket, and the same stones radiate their heat back into space, plunging into a deep, penetrating cold. This daily cycle is not a gentle shift, it is a relentless physical assault. Most solid materials, including the granite the Inca used, expand when heated and contract when cooled. In a conventional, rigidly mortared wall, this constant push and pull creates immense internal stress. The different materials, stone and mortar, expand at slightly different rates, and over years, this silent, daily battle creates microfractures. Water seeps in, freezes, and widens the cracks, a process that steadily weakens the structure from within long before any earthquake arrives. The Inca walls, however, were designed for this conversation between stone and sky. Those famously tight joints hold a secret allowance. While a knife blade cannot slip between them, the fit is not one of absolute crushing pressure. There exists a microscopic tolerance, a space measured in the width of a hair or a grain of sand. This was not a flaw in their precision, but its highest expression. It created a system of controlled movement. As the sun warmed the face of the wall, each stone could expand minutely, pushing gently against its neighbors. Because they were not glued in place, this pressure did not build into a destructive force. Instead, it was distributed across the entire network of interlocking faces, absorbed as friction and tiny, permissible shifts. When the cold night caused contraction, the stones could settle back into a slightly different, yet still perfectly supported position. The entire wall could breathe, flexing with the temperature as naturally as the mountain it was carved from. This reveals a fifth, brilliant principle in their design: thermal expansion management. They were not solving for just one catastrophic threat, but for the slow, grinding wear of everyday nature. Their architecture accounted for the entire cycle of stress, from the sudden, violent shake of a quake to the silent, daily pulse of heat and cold. It was a multi-hazard design philosophy crafted centuries before the term was invented. They understood that true endurance meant building for all of nature's rhythms, designing a system that could dance through both the sudden temblor and the eternal, patient heartbeat of the sun. The walls stand as a monument to physics, but they were born from a triumph of human organization. This technology did not rise from the quarries by itself. It was powered by a social engine so effective it could move mountains, stone by stone, known as the. This was not slavery, but a foundational principle of the Inca state, a form of labor tax where every community contributed a rotational period of work to public projects. Imagine the logistics required to shape and place a single 100-ton block. Now multiply that by thousands. The system provided the answer, mobilizing a vast, coordinated workforce drawn from across the empire. One group would specialize in quarrying, using fire and water to fracture the bedrock. Another immense team would focus on transportation, maneuvering the colossal stones along earthen ramps with nothing but ropes, levers, and log rollers. A final contingent of master stonemasons would then begin the patient, generations-long process of fitting. This was a society that understood its greatest resource was collective effort. The precision of each polygonal joint is mirrored by the precision of the logistics that made it possible. A stone cut in a distant quarry was not just a piece of rock, it was a unit of labor, a fulfilled obligation, a thread in a social fabric woven tight enough to bind granite together. To see only the interlocking stones is to miss half the picture. The true foundation of these earthquake-proof walls was an interlocking social contract, a network of reciprocal duty that turned a common purpose into an unshakable reality. It reminds us that the most resilient structures are always, in the end, built by communities. A perfect fit can feel like magic. When something is so precise, so seemingly impossible, the human mind instinctively reaches for explanations beyond the ordinary. Over the centuries, the silent perfection of the Inca walls gave birth to beautiful legends. One persistent story speaks of a magical plant, a juice or sap that could temporarily soften granite, allowing the builders to mold the stones like clay before they hardened again into their eternal forms. Another tale suggests the stones were somehow melted and poured into place, a liquid rock that cooled into these intricate puzzles. These are captivating ideas, born from a place of deep awe. They are a testament to the emotional impact these structures have always had on those who witness them, a recognition that what was achieved feels, on an intuitive level, supernatural. While there is no botanical or geological evidence to support these stories, they serve an important purpose. They highlight the very gap in understanding that we are now trying to close with science, not myth. They mark the boundary where wonder meets the need for explanation. Moving from legend into the realm of serious research, we find theories that are less magical but no less fascinating. Researchers like Jean-Pierre have spent decades in the field, experimenting with the tools the Inca had available. His work suggests that the incredible shapes were achieved through a process that was astonishingly straightforward, yet required immense patience and skill. It likely involved the repeated pounding of stone against stone. A builder would strike a selected granite block with a harder hammerstone, not to smash it, but to strategically fracture it along its natural grain. This was followed by the relentless grinding of the surfaces against each other using sand and water as an abrasive. Think of it as the world's most labor-intensive sanding project. This theory does not diminish the accomplishment, it reframes it. It replaces a lost magical formula with a demonstrable physical truth, the cumulative power of human perseverance. Exploring these myths and serious alternatives is a crucial step. It separates romantic fiction from the even more impressive reality. The truth is not that the Inca possessed a secret they took to their graves, but that they mastered a public, repeatable technique through generations of refined practice. The magic was not in a plant, but in the collective will to execute a vision with such unwavering dedication that the result still whispers of the impossible. This grounding in evidence does not strip the walls of their wonder, it redirects our awe toward the human hands and minds that conceived them. It forces us to confront a humbling reality, that their greatest technology may have been a cultural capacity for focused, generational effort that we struggle to fully comprehend. In the heart of modern, the past is not a ruin, it is a foundation. Walk its cobbled streets, and you will see colonial balconies and modern shopfronts rising seamlessly from ancient, curved walls of polygonal stone. This is not a coincidence or a compromise, it is a conscious choice that has saved lives. For centuries, people here have built their homes and businesses directly upon the unmoving shoulders of Inca masonry, recognizing its unparalleled stability. When powerful earthquakes have struck in recent decades, this practice has proven its worth. Time and again, modern structures anchored to those old foundations have survived, while others built on less stable ground have suffered far greater damage. The walls are not relics behind a rope, they are active participants in the city's life, bearing new weight just as steadfastly as they bore the tremors of centuries past. This creates a profound, daily relationship with history. For the people of Peru, these stones are a constant reminder of ancestral ingenuity, a physical testament to a knowledge system born from deep observation and respect for the land. This living legacy actively shapes contemporary thought. Modern Peruvian architects and engineers study these walls not just as archaeology, but as a master class in passive seismic design. The principles of flexibility, interlocking geometry, and foundation integrity observed in the ancient sites are now inspiring new approaches to building in a country that will always be earthquake country. There is a growing movement to blend this traditional wisdom with modern materials, creating structures that honor the old intelligence while meeting new needs. This represents a continuous, unbroken lineage. The technology did not vanish. It simply waited, embedded in the landscape, for a new generation to rediscover its logic. It connects past and present in the most tangible way possible, not through a museum display, but through the very ground people live and work upon. It offers a powerful model for the future, demonstrating that building in harmony with a volatile environment is not about conquering nature, but about learning its rhythms and designing with humble, resilient grace. Their legacy offers a quiet but urgent blueprint for our own turbulent century. As we face a future of intensifying climate events and more frequent natural disasters, the principles embedded in those ancient walls speak directly to the core challenges of modern design. The Inca achieved something we now strive for: true sustainability, not as an added feature, but as the foundational purpose of their architecture. They began with local materials, using the very granite of their mountains, shaped with minimal processing that required no imported chemicals or high-energy manufacturing. Their structures were built for permanence, designed to endure not for decades, but for centuries, drastically reducing the need for reconstruction and the constant consumption of new resources. Most critically, they designed for disaster resilience from the very first stone, integrating seismic safety into the fabric of the building rather than adding it as a costly retrofit. This holistic view stands in stark contrast to much of our contemporary approach, where sustainability and resilience are often separate, expensive checkboxes. The Inca model shows they are inseparable, two sides of the same coin. A building that lasts 500 years without needing to be rebuilt is inherently sustainable. A building that uses the physics of its own form to survive a catastrophe avoids the immense waste of collapse and reconstruction. Their work demonstrates a profound truth: that long-term resilience does not always demand complex, energy-intensive technology. It can be achieved through intelligent design, a deep understanding of material behavior, and a fundamental respect for the natural forces at play. This is not about romanticizing the past or abandoning modern innovation. It is about recognizing that some forms of intelligence are timeless. The self-locking joint, the tapered seam, the flexible collective, these are design principles that transcend their medium. They encourage us to think in terms of systems rather than isolated components, to build structures that are adaptive and forgiving. Imagine applying this philosophy to the materials of our own time, to concrete, steel, and composite polymers. What would a modern building look like if it were designed as a cohesive, interlocking system meant to flex and settle? What if we prioritized passive safety, where the structure's very form manages energy, over active systems that can fail when the power goes out? The Inca walls challenge a persistent myth that a safer, more durable future must be more technologically complex and resource-hungry. They offer a counter-narrative, one where elegance and simplicity, born from careful observation and cultural commitment, create the most enduring strength. Their silent stones ask us to reconsider what we mean by progress, suggesting that sometimes the most advanced path forward is to understand the deep wisdom already written into the land. There is no single stone you can point to as the beginning. In the grandest Inca walls, you will search in vain for a traditional cornerstone, that singular, ceremonial block upon which the entire structure is symbolically and physically anchored. This absence is not an oversight. It is a sixth, radical principle etched into their very philosophy of construction. The stability of the wall does not radiate outward from one privileged point. Instead, it emerges from everywhere at once, from the continuous collective interaction of every polygonal block with every other. Think of it as a society in stone, a true democracy where each member is essential, but no single member is irreplaceable or supreme. The strength is in the network, in the countless relationships of pressure and support. If one stone were to be removed, the geometry of its neighbors would redistribute the load, preventing a catastrophic collapse. This challenges a deep-seated instinct in how we think about building, both physically and socially. We are accustomed to hierarchical designs, a pyramid with a keystone, an organization with a single leader, a story with one hero. The Inca wall proposes a different model, one where resilience is a distributed property. It suggests that ultimate strength is not found in creating one unbreakable component, but in designing a system where the connections themselves are the source of durability. This principle echoes far beyond archaeology. It resonates in the robust structure of the internet, designed to root around damage. It appears in healthy ecosystems that thrive on biodiversity, not on a single dominant species. It is present in communities that draw their resilience from mutual aid and deep social bonds, rather than reliance on a solitary figure. The wall becomes a silent teacher, reminding us that in a world of constant stress and shock, whether seismic or social, our greatest security may lie not in a stronger cornerstone, but in building better, more intelligent connections all the way through. A wall that survives 500 years does more than hold up a roof. It holds up an idea. For the descendants of the Inca, these structures are not silent ruins. They are active ancestors. They are a physical handshake across centuries, a direct, unbroken connection to the skill and vision of those who came before. In a world that often feels ephemeral, built on digital data and disposable goods, these stones assert a powerful counter-narrative. They are the ultimate proof of concept for human perseverance. They whisper that stability is possible, that continuity is not just a hope, but something that can be intentionally built, stone by patient stone. This provides a psychological anchor, a deep, often unspoken comfort. Knowing that your great-grandparents and their great-grandparents before them walked beside the same unmoving wall that you touch today creates a profound sense of place and identity. It roots a community not just in a location, but in a demonstrated legacy of resilience. The walls become earthquake-proof for the human spirit. They stand as a bulwark against the tremors of time, against the erosion of memory and the chaos of change. When modern life feels uncertain or transient, the enduring presence of such craftsmanship offers a quiet, monumental reassurance. It tells us that some things, built with enough care and collective purpose, can truly last. This emotional dimension is not a side effect. It is central to the technology's enduring power. The precision of the cut, the intelligence of the interlock, these are not cold engineering facts alone. They are expressions of a cultural commitment so deep it sought to make values like harmony, cooperation, and patience permanent features of the landscape. We are captivated by the walls because we recognize in them a profound human yearning, the desire to create something meaningful that outlives us, to speak to the future in a language of stone. That is why they inspire awe generation after generation. They are not just puzzles from the past, they are promises of what enduring human effort can achieve, invitations to consider what we, in our own time, are building for the centuries to come. The greatest threat to these walls is not a sudden tremor, but a slow, creeping pressure. After surviving centuries of earthquakes, the stonework now faces a more insidious enemy, the modern world. Exhaust from dense city traffic coats the granite in a corrosive film of chemical pollution. The vibration from constant construction and heavy vehicles transmits subtle, damaging shocks through the ground. Urban expansion pushes right up against the ancient foundations, altering water drainage patterns and putting physical stress on the structures. Ironically, some of the most significant damage has come not from neglect, but from past attempts to help. For much of the 20th century, the standard approach to preserving old stonework was to use modern cement mortar to repoint joints and stabilize leaning sections. This well-intentioned effort fundamentally misunderstood the Inca technology. Pouring rigid cement into the flexible, self-locking joints is like putting a cast on a living limb that needs to flex. It traps moisture behind the stone, causing internal erosion. It creates hard points that concentrate stress during an earthquake, precisely where the original design sought to dissipate it. These old repairs, now crumbling and stained, stand as a stark lesson in the danger of applying modern assumptions to ancient intelligence. The conservation challenge itself highlights the system's radical uniqueness. We are learning to care for a form of engineering so advanced that our standard preservation toolkit can be actively destructive. This demands a new kind of humility from us. Today, preservationists and engineers work with a principle of minimal intervention. They use invasive techniques like 3D scanning to monitor the slightest movement over time. When stabilization is absolutely necessary, they seek out compatible materials, sometimes even grinding local stone to create a similar mortar that behaves more like the original stone, allowing for some breadth and flex. The work is painstakingly slow, often involving the careful removal of damaging old cement, grain by grain, to liberate the original joint. This meticulous process is a form of reverse engineering in real time, a dialogue with the builders of the past. Each decision is a balance between preserving the authentic fabric of the site and ensuring it remains safe for the public who come to witness its wonder. The goal is no longer to freeze the wall in time with a rigid embrace, but to safeguard its inherent ability to move, settle, and endure, just as its creators intended. Protecting this legacy requires us to first understand it on its own profound terms. From the seismic heart of the Andes, the Inca gifted us in resilience, written in stone. Their interlocking technology is a profound conversation between human ingenuity and an unstable earth. It shows us that true strength does not come from an unyielding stance, but from an intelligent, flexible response. Each polygonal puzzle piece, each tapered joint, and each foundation carved from bedrock speaks to a philosophy of building that embraced movement, distributed force, and deep respect for the material and the moment. These are not static monuments to a lost past. They are active, enduring teachers. They instruct us in the physics of dissipation, where energy is transformed into friction instead of fracture. They offer a philosophy of community, where the integrity of the whole emerges from the perfect fit of every unique part. And they provide a timeless model of sustainable design, where longevity and disaster resilience are woven together from the very start. As we navigate our own modern tremors, both the literal shaking of the ground and the metaphorical upheavals of our time, these silent stones hold a quiet counsel. They remind us to build with foresight, to design systems that are adaptive and forgiving. They encourage us to seek strength in intelligent connections, in networks that can support and redistribute weight. And above all, they ask us to work in harmony with the fundamental forces around us, not in a futile battle against them. The legacy of the Inca walls is not locked in the past. It is a living blueprint, waiting in the landscape for anyone willing to learn its language. If you found this journey into ancient engineering fascinating, subscribe for more explorations into history's greatest mysteries. We would love to hear what these enduring walls mean to you, so please share your thoughts in the comments below.